Since we have now established that some nebula are basically birthplaces of stars or star nurseries, it might be worth we take a quick look in the star in these nebulas and how to classify them. So share screen to go up. Yep, that's done. That's done. So okay, so back to change this and help me a bit. So basically what you have seen in the video fully was the Orion Nebula that you see here again. And what we see in these pictures is often something reddish, but we have to be careful, of course. These pictures might be colored afterwards. It's not necessarily that these are photographs in the optical region with the colors as we would experience it. And of course, I can't feel with the people who have a red-green weakness because I don't have it, hopefully. So sorry if you have it. Nevertheless, the rest of us sees here this nice reddish. Then what we see around stars often is that the gas is a bit bluish, so next to intensive light sources. But we have here again to be careful, is this maybe just an artifact coming from the optics, that the lens maybe makes this blurry and appears, and this is called chromatic aberration, that sometimes light is in a lens, of course, split, the same as in a prism. And then we have seen, towards the end, you have seen the Horsehead Nebula. Or I still, for me, it looks more like a cobra, but maybe once you have something in your mind that it stays with your mind, and hard to convince otherwise. At least me, I'm quite stubborn. So, and then we occasionally see a few other colors, but again, we have to be very cautious with this. Astronomers and their color coding. So some of these nebulas have an object in the center, as we have seen, a white dwarf can it be. Some have a neutron star like the Scrap Nebula. And they are usually the corpse of a star. So the rest, what you see around, is basically most of the material of the star that have been blasted somehow into space, forming then this nebula. But there are also much bigger clouds, far, far bigger clouds. So in some, these are occasionally just clouds of occasionally ionized, but of course also atomic gas. And if we talk of hydrogen, atoms, well, are not the natural state of hydrogen. Hydrogen likes to form molecules, H2 molecules. Or occasionally, if then there's a catalysator nearby and we have some oxygen already, then of course H2O, water, which is obviously very stable. Otherwise, we wouldn't have so much of it on our planet. Would be then dissociated in H2 and O. And oxygen, of course, also atomic oxygen is hard to find. It's usually also as molecule as O2. So two atoms combined. Okay, but we have now seen there are three different colors, mostly the blue. And we would talk about the reflection nebula. A red, then it's an emission nebula. And black, we talk about an absorption nebula. Or means no visible, sorry, here's no written light, but it should be no visible light comes from or passes through. Other colors, well, there might be emissions from other chemical elements that have been produced, for example, in the Crab Nebula, in the last stages mostly of the stars, and when it was dying, in the process of dying. Okay, so these colors again, red, this would be the emission. This is the reflection part, and blue, obviously nearby intensive light sources. Here it appears at least some yellowish in. Yellowish is usually, for example, I would associate sodium. Sodium is if it's made shining, it's intense yellow. These are the so-called sodium dealer and the white mice of atomic physics. By the way, if I say natrium, I mean sodium. It's just that's where Na comes from. That's a German word that occasionally happens to me. Potassium, I often call kalium, K. You know where the chemical symbol comes from. Oh, that happens. Well, and it happened to me when I was working together with an Indian colleague, and she looked at me because of Kali, this Indian goddess of death. Yeah, intercultural misunderstandings. So these are the other chemical elements. This means here must have some cataclysmic event must have happened if these elements are present. But yeah, and then of course the Horsehead Nebula itself is so dense, there's the light not coming through. Well, in the reflection nebula, obviously, there is some light scattered. There is a light source and it must be scattered. And blue light scatters more than red light. This is, for example, why our sky appears blue, which we can now look at. So in the prism, this would be the white light with all wavelengths comes along. And now the blue light, because it scatters more, it's basically more deflected. Therefore, appears on this side, and with less of a scattering angle comes the red light, yellow, green, blue, violet. So obviously, violet scatters a bit more blue. And then we get it nicely divided in the prism. And of course, here this angle again, we get another scattering. In fact, the physical process is called dispersion. The refractive index is depending on the wavelengths. That is called dispersion. And how does this work now in the sky? Well, the sun obviously sends the sun is a bit further, of course, away. Oh, sorry, I forgot again to make the laser pointer. So, blue light, red light. Well, because the blue light is scattered more, we get more from more direction than we get the red light. The red light is basically coming just under small angle scattering, and we get more blue light. See, that's why blue dominates in the sky during the day. Or during the day, sun comes from, the light comes almost above, and then we get the light, of course, scattered from all directions. It appears blue. And now we go in the evening. The blue light scatters away, the green light scatters away, and then what we see in the evening, just before the Earth rotates now in such a way, yep, it rotates in this direction. So, yeah, sun rises in the other way around. So this is in the morning. Sorry. So in the morning when you're in Hawaii, somewhere, or North Pole, what happens is the blue light is scattered away, the green light is scattered away, and what you see is the red light. So this is why in the evening, in the morning, the sky appears to be reddish, because the other light is missing. Once you get an excess and once you get deficiency. Okay, so nearby an object we have then this blue light because it scatters more than red. It means we get it directly as well as the scattered, which would be emitted somewhere else and then scattered towards us. And then there comes another effect, at least for young stars, which is often in the case in nebula, that the stars that are there are relatively young. If they are nursery, it means what is there is often freeborn, newly born. If you go to a nursery in a hospital, the average age is obviously drastically lower than if you live next to retirement. So you have there more very young star. What happens that the outer layer haven't really settled yet? What means we can look, it's less opaque. And we can look deeper. And deeper means hotter. More pressure, the gas is pressure equals temperature, the gas is hotter. Hotter means from the Planck spectrum, it must be shifted towards the high energy side, the UV light. It means there comes also already more energetic blue light out than later from a star where then actually everything has settled and we are basically in equilibrium. So younger stars, often this UV light, and then we can have anyway more scattering, we get more bluish or violet bluish light. So that's another reason. Okay, well, this is basically already explained why the baby stars, the freshly born, its surface layer is less opaque. Didn't settle really down yet. Oh, well, what also can happen is that the UV light basically is so energy rich that you can ionize or heavily excite the light. If it's ionized and you recombine, you get again UV light, except you are going towards the second of these pores radius. If you come from totally outside, you come with violet and then bluish. If you just have excited to the third one, you get this red light. But this would be, for example, happen if you have thermal movement of these hydrogen atoms moving around and collide. So again, when you had these ionization processes, because you had a very intense UV light source nearby, then you would get again more bluish because you get usually then this recombination. Most of it would be ending up here and it sends out UV light, which we don't see. But would also be this bluish more. While if you have just gas and there are collisions, what happens is that you come from the ground state and you might excite rather to the third than to the fourth or fourth. That means if you have the third, most of it again will decay rather to the ground state, but to good fraction, it also decays to the second excited, and this would be just this typical red light. Voila, and the stuff shines with this characteristic red of hydrogen. By the way, from this nebula that we are talking at the moment, we talk about nebula in our own galaxy and maybe in Andromeda and very nearby galaxies, so we don't have to consider this redshift from cosmology. Because otherwise we can't resolve them in different galaxies that are more than 50 to 100 light years away, forget about it. A million light years away. 50 to 100 light years, we are still in our galactic neighborhood. Okay, and then black is, of course, when everything is absorbed. The light that is produced behind can't make it through in itself. It doesn't shine in the optical, but if we would look in the infrared or microwaves, we might still see something. The star nebula, obviously, very dense. Very dense means very loads of gas, loads of material. This is really where the stuff goes on. So there are a couple, or there are plenty of them. This Barnard 68, wherever this name comes from. We have this very dense region, and it appears basically almost like a hole in the night sky. There are no stars, but it's just because this is in the foreground and blocks away the light of the stars. The same is here with the Snakehead Nebula, whatever B72 means. So this is basically gas that is so dense that you can't see through. But then if you look in different light, like infrared, here again the Horsehead Nebula and the optical. And then we look in this nebula with the infrared. This is this stuff here. And then we see here these dots. Well, here we also see this dot a bit, but we see also smaller dots that we would otherwise not see. And if we take this look every 2 or 3 years, you see there are new dots. So with this infrared, we basically can see through the dust. Oh. Then other nebula where similar is going on. This here is again optical. That's the so-called Rho Ophiuchi dark cloud. So this stuff here, obviously. In infrared, this here is still in optical, so it's dark cloud. Here's Antares. So if you find Antares, then you know that nearby there is basically this cloud. And inside there, well, if we take a look with infrared, the same stuff basically. And obviously here is Antares now blocked away. So this in infrared with Spitzer Space Telescope. Then we see all this little pop, this little how to say, these little babies. So really a vast number of stars that are born together. It's a bit like which species of animals, spiders, for example, they always have these thousands of offspring all at once, or meerkats, or loads of baby stars, all in this cloud, hidden in this cloud. Okay, so we have clarified some of these nebulas are really star nursery, and then it's not one, it's plenty of them. And obviously somehow this gas needs to contract in order that we have locally a very dense object like our sun. Well, the surface is not so dense, but if we go deeper and deeper and deeper, the more dense it becomes. And at some point it's so, even Jupiter, a gaseous giant, mostly gas, but at some point the pressure in this gas, because you have so much, the gravitation has become still very high. And at some point the pressure is so high that we can liquidify nitrogen and hydrogen, which is something that on Earth we need. The last couple of years we have achieved it, but took us quite a while. So obviously it needs quite some technological input. And we have the massive pressures inside just by gas, by accumulation of gas or plasma then in the star. So, and how do we form? Basically from a cloud. This video shows now a simulation where you basically have a gas cloud and it starts collapsing, and we have local density fluctuation, which then forms seeds to accumulate more and more matter. And then you see that locally we had some kind of rotation in the gas. And this will then cause this spinning, also the infalling gas. And what we also see, there will form what is called some accretion disks. So instead of having a spherical and contracting, sphere contracting, it's rather what builds out is some kind of disc-like shape, but discus that is rotating. So this is shown in this video, and I would say I stop now my video, and then you can have a nice look at this video. Go and get yourself a coffee, get yourself a break from me and my voice, and then tune in when we explain or go step by step what is happening when the star basically forms. From gas cloud contraction towards well, a plasma sphere. So see you then in a few minutes.